Hello, welcome back. Not at home. This is recorded in 2021. So, whoops. Here's chapter 11. We are about to get into what is our last unit, dealing with relationships between two variables. So, we've already talked about this some, or I will talk about with you soon in person about what's the idea here in chapter 11? We're looking to find the relationship in chapter 11 between two qualitative variables. So relationships between qualitative variables. So we're going to be talking about qualitative variables here in 11, and then when we get to 3 and 12, we're talking about quantitative variables. Qualitative variables are going to be on a two-way table. You got yes, no, yes, no. Variable one, variable two. You got two qualitative variables. So that's what we're going to be talking about here, relationships between qualitative variables. And then next part of the unit, we'll get into 3 and 12, relationships between quantitative variables. What's that going to look like? It's going to look like a scatter plot. So you have vocabulary here. It's really not that many things. You're going to find, I think, that a lot of these can be bundled into one or two cards. The goodness of fit test is its own thing. The chi-square test for association independence, that's its own thing. Homogeneity test, that's its own thing. There's really not that many things there. A few big note cards would be my suggestion. So we're getting into 11.1, inference for distributions of categorical data. We've got the word here, categorical. I might rewrite that as qualitative. So we're going to talk about qualities. Qualities. Does it have this quality? And what is your response to having a quality? Often yes or no, or what quality do you fall into? Or what category do you fall into? So what is chi-square? First off, chi, not chai, not chi, but chi. Chi-square distributions. It's a Greek character. Chi-square looks like this looks like a fancy X. So that's the Greek letter chi. Some of the religious amongst you might have seen like this symbol somewhere along the way, like a chi and a rho stuck on top of each other. That's something, something short name for Christ or something. I don't know that much. But Greek characters, that's the Greek character chi, and you might you make the left side kind of fun and the other side straight. So boom, 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 boom. So make sure you can make some chi's. That's the first thing, a new symbol for us. So up until now, we've only conducted formal inference about parameters, such as estimating proportion or a population proportion, population mean or population proportion. But what if we wanted to answer questions like, is the distribution correct? Do people on different campuses use something differently? Purebred dogs resemble their owners more than mixed breed dogs. So these are not questions about a single parameter, but these are questions about whole distributions. Not questions about a parameter, questions about distributions. So we're not going to be talking just about a single parameter, the mean or the proportion, but we're going to be talking about how the entire variable is distributed, or how it's distributed within a population. So today we're going to be talking about the goodness of fit test. Goodness of fit test is used to do what? To help determine whether a population has a certain hypothesized distribution. Is the distribution right? Is this the right distribution? This is a question of kind of, is this the right distribution? And so we'll ask ourselves, does this seem to match up with what is specified by some hypothesis, or is this too far away for us to say, is this good? So our hypotheses for these tests, we've got a null and alternative hypothesis for the goodness of fit test. I'll sometimes call this the chi-squared Goff test, and that's what it looks like in your calculator, Goff, goodness of fit. The null hypothesis, the stated distribution is correct. The stated distribution is not correct. So that's a little different than usual. We're going in assuming it's right. Actually, it's not any different. We go and assume it's right, and we need evidence to say it's wrong. We need evidence to say it's different from the specified distribution. So what is this chi-square thing? Well, this chi-square statistic, here's your chi-square. How do we find chi-squares? We add up. Remember, this big sigma means we need to sum the observed count minus the expected count squared. So that's the kind of the squared deviation from what we expected divided by what we expected. So what does each part of the chi-square statistic show you? The numerator, that's kind of like the absolute deviation. And then when we square it, that's going to make it positive. The square part makes it only positive things. And the denominator kind of like scales the error relative to how big the group should have been. So it's like, how far away were we? We want them to all be positive, so we square it. So we've got a sum of squared deviations in the numerator, and the denominator. It's kind of like we're kind of scaling it. We're saying, oh, how big should it have been? Because if I get a big deviation, but it was a really big component, I might be expecting that. But if I have what should be really small expected component and it ends up having a really large error, that tells me, oh, this is really significant error. Scales the error relative to the expected count. Whatever. So we're going to have to calculate these, and these are statistics we can count, as opposed to some of the other stuff, the t statistics. Sometimes that was a little harder. Sometimes we didn't calculate that by hand. But chi-square stuff we can calculate by hand. So let's jump into it. We have on our next page the expected counts. How do we find these expected counts? Well, let's see. To see if the data give convincing evidence against the hoe, we compare the observed counts from our sample with the expected counts, assuming the hoe is true. If the observed counts are far from the expected counts, that's the evidence we're seeking. How do we find the expected counts? We multiply the sample size times the hypothesized proportion. So that's the sample size. P naught is the hypothesized proportion. But we're going to have a bunch of hypothesized proportions, so I'll call that the hypothesized proportion for the ith category. We're going to have a bunch of categories. We're going to have colors of cars, days of the week you're born, whatever. Well, you need to multiply the sample size times the hypothesized proportion for that category. So what are we looking for? What are our conditions to perform this test? We still have our randomness condition. Random sample or randomized experiment. Remember, that's to eliminate bias, reduce bias. Independence condition, we need independence. Is a sample less than 10% of the population? And now we don't have the normal condition anymore because we don't have a normally distributed sample statistic. We now have a chi-square sample statistic. So we're going to use this large counts thing. All the expected counts are at least 5. So that's a new one. Expected counts at least 5. Great. So you're asking, what do I know about this chi-square distribution? I don't know anything about this thing. We're not going to talk a ton about it, but we do have this chi-square table on the back. We'll use this in conjunction with our calculators to calculate p-values and compare them to alphas and draw conclusions about whether we can conclude or what we conclude, what we can't conclude. So we've got our conditions for our chi-square test. Chi-square distributions. The chi-square distributions are families of distributions that take only positive values and are right skewed. You'll notice that the squared distance from what we expected can only be positive, and there's going to be a lot more values close to 0 than there are values far away from 0, the extreme values. So down at the bottom, we have something here called degrees of freedom. The degrees of freedom for goodness of fit test are going to be n minus 1, where n is the number of categories. So that'll help us. You can see on here, um, as we have more categories to choose from, we might see that we expect to see a little more of a chi-square statistic. So this tells us kind of here, as we have more categories, it's going to take a larger deviation from what we expected to be able to reject, because naturally, as you have more categories, there's going to be more variability between those categories. And so there's going to be more categories that don't hit the target. But that doesn't mean it's wrong. It just means we might need to look a little bit harder. How to find a p-value given a chi-square statistic? We have this chi-square CDF down at the bottom. This is analogous to your norm CDF and your T-CDF, like we've seen. So we can find probabilities of given chi-square statistics using our chi-square CDF, or we're going to actually just use our calculator in the chi-square test more often than not. So let's do a problem here. Janie made a 6-sided die in her ceramics class. Great. And rolled it 60 times to test if each side was equally likely to show up. Equally likely to show up. The table shows the results. Okay, state the hypotheses Janie wants to test. What is the evidence for ha? Well, part A, or ho, is that what? The sides on your die were equally likely. So you can write it in words, or you could write it P1 equals P2 equals ... equals P6 equals 1/6. So you could say that each side on the die has 1/6 probability. They're the same statement. Your ha? Sides aren't equally likely. Or you could say at least one pi not equal to 1/6. So you can get away either way. Do you like in words? Do you like in parameters? I don't really care either way. You're fine. So there's your part A. Part B, calculate the chi-square statistic. Oh my gosh. Well, we need to first say what was expected. What was the expected count? Well, what is 1/6 times 60? That's 10. So we expect to have 10 for each of these sides, right? If they're equally likely, we better have 10 for each. So we have our expected counts, we have observed counts. With that, we can calculate our chi-square statistic. So part B here, chi-square is the sum of the observed minus expected squared over expected. These are all going to be over 10, which is kind of nice. So this is going to be, whoopsies. This is going to be 13 minus 10 squared over 10. That's for 1. We have 11 minus 10 squared over 10. That's for 2. We have 6 minus 10 squared over 10. That's for 3. We have 12 minus 10 squared over 10. That's for 4. You can keep doing this. 10 minus 10 squared over 10 for 5. That gives you no contribution. And for 6, it's going to be 8 minus 10 squared over 10. Cool beans. All right, so that's our chi-square statistic. We add all those up. We do a little math. That's not so bad at math because it's got a denominator 10 and numerator is going to be the square of whole numbers, so I can do that. 9, 10, 16, 20, 24. So what is that going to be? 24 over 10 is 2.4. So if I did that math right. Did I do that right? 9, 10, 4 squared is 16. Oh, no, I didn't. 9, 10, 4 squared is 16, makes 26, 30, 34. Okay, that's right. 3.34 over 10 is 3.4 for our chi-square statistic. 3.4 is our chi-square statistic. Okay. How many degrees of freedom does this have? Degrees of freedom is n minus 1. In this case, it's 6 minus 1 is 5. I'm going to write that 5 down here on my chi-square because typically we're going to write this thing as chi-square with our degrees of freedom down there, the denominator. So I'll write this thing as a chi-square with 5 degrees of freedom. Part C, it asks me to find the p-value. I can do that one of two ways. I could either use my chi-square table. We'll use this real quick. I see a degrees of freedom of 5. And then I go until I find my value. Well, 3.4, it'd be somewhere out here. So that'd be a p-value. Well, these are p-values smaller than 0.25. As I get bigger bigger chi-square statistics, I have smaller p-values. So if I go the other way, I must have a larger p-value. So my p-value from the table shows me a p-value that's got to be greater than 0.25. If I did it with my calculator, that'd be chi-square CDF, lower bound, upper bound, mean, standard deviation. Let's do that real quick. We can go on here, hit second vars, pull up our stat distribution menu, go down to chi-square CDF, hit that. Lower bound 3.4, upper bound bunch of 9s, degrees of freedom is 5, paste it and get an answer. And we've got a p-value of 0.638. 3.4, bunch of 9s, 5. We get a p-value 0.6386. So either way, we have a very large p-value. Let's think about what that means. If you rolled a die 60 times, I personally would be weirded out if it came out 10, 10, 10, 10, 10, 10, 10. You might be too. Maybe not. I don't know. I don't know. I'd be weirded out because I'm not going to get exactly that result, but there's going to be some deviations. I don't expect it to be 10, 10, 10, but I expect there to be a little variation. How weird is this variation? This p-value tells me that this is pretty normal variation. I'd get deviations from what I expected, this large or larger, about 64% of the time. That happens all the time. So that's a very high p-value that would lead us to fail to reject. Part D, since our p-value is greater than any alpha, we fail to reject. Not enough evidence to say the die doesn't appear likely, isn't equally likely. To show up on each side. All right, and then part E, what type of error might we committed? By failing to reject, we may have committed a type 2 error, failing to reject a false null. And then part F, what contributes the most? Go back, my Mike Tyson all of a sudden. What contributes the most? Go back and look into your chi-square statistic and see which one of those added the most. Well, I'm looking up here, and this is the one that was 16 over 10. This was 1.6. So these are like 0.9, 0.1, 1.6, 0.4, 0, 0.4. So you can see the largest one there is 3. That is the largest deviation, the one that was furthest from what we expected. This had the largest contribution. So we can calculate some chi-square statistics. We can say how far is this from what we expected. Eventually, we'll be able to check some conclusions or check some conditions, and this looks very similar to what we have been doing. Couple examples for you here. On the next page, it tells you the chi-square goodness of fit test on your calculator. It gives you steps for this. The one thing I will say, uh, what do we need here? Your observed frequencies are in L1 and your expected frequencies are in L2. So that's an important thing to note. Those of you who don't have a TI-84, you might need to check one out. This is not on your TI-83. TI-83s don't have this program. So if you want to have the goodness of fit calculator on your, goodness of fit function on your calculator, you're going to need to check out one of the TI-84 pluses from the library, or you're going to have to do it by hand. And you can. So let's do this one last example. Is this last example, right? Yes, last example. We're going to do this in the calculator, show you how this works. So does the warm, sunny weather in Arizona affect a driver's choice of car? Cass thinks that Arizona drivers might opt for lighter cars, hoping to reflect some of the heat from the sun. To see if the distribution of car colors in Oro Valley is different from the distribution of car colors across the North America, she selects a random sample of 300 cars from Oro Valley. All right, the table shows the distribution of car colors in Cass's sample and the distribution of car color in North America. Do these data provide convincing evidence that the distribution of car color differs from the North American distribution? So, null hypothesis. The distribution of car color in Oro Valley is the same as the North American distribution. And the ha is that the distribution of car color is not the same in Oro Valley as the North American distribution. Okay, so we've got our null and alternative hypotheses. The null hypothesis is that Oro Valley is the same as everybody else. No difference. Null. Null means nothing. There's nothing there. So null hypothesis, there's nothing there. Oro Valley is the same as the larger North American car population. But the alternative is not. It just needs like a no in there somewhere. All right. So that is our state step. Our plan step is going to be to perform a chi-square goodness of fit test. Our three conditions are that we took a random sample. What else do we have? We have independence of trials. That is, our sample size is less than or equal to population size divided by 10. Similarly, we could say there's at least 3,000 cars in Oro Valley. Where did I get 3,000 from? 10 times 300. And we need that last condition, which is our large sample size condition. And we need all our expected counts to be at least 5. So I'm going to say that all expected counts are greater than or equal to 5, but I need to show those expected counts somewhere. And this table up above gives me a pretty good place to put my expected counts. My expected counts, I have a total of 300. Well, a percentage is per 100. So if I multiply 0.23 times 300, I can actually just multiply these percentages by 3 and get my expected count of 69, of what is that, of 54, of 48, of 45, 30, 27, 6, and 21. Again, I'm getting all those values by multiplying n times the hypothesized proportion. In this case, that's 300 times the hypothesized proportion. So 300 times each of those percentages will give you those numbers I've written down below. And you'll notice that those are all greater than or equal to 5, so the condition is met. You might be saying, what's this greater than or equal to 5 business? Well, if something has a very small expected contribution, it can lead to very large chi-square deviations. I'm going to wave my hands about that much and say that's good. So we stated, we've planned. Now we're going to go ahead and do, but we're going to let the calculator do the do step for us here. Let's do that. Going to go into our stat and our lists. Haven't touched this in a while, perhaps. Going to clear out list 1. Remember, don't delete the list. Hit clear on the list and then go down. And in L1 are going to be my observed counts. So this is 84, 38, 31, 46, 27, 29, 6, and 39. And then I'll go and put my expected counts in list 2. Where am I getting those from? We just wrote them up above. Those red numbers, I'll write them so you can see a little more easily this time. That is 69, 54, 48, 45, 30, 27, 6, and 21. Boom. So it's nice when our lists are of the same length. That tells us we've done something right, or at least done something consistently wrong. We can quit out of that. Go ahead and look at stat. We're going to go over to the tests. I'm going to hit up and go to option D, the chi-square goodness of fit test. Those of you with a TI-83, one of these guys, are realizing right now that you don't have a calculator that can do this thing. So you need to check a new one out. We'll do this chi-square goodness of fit. Observed in L1, expected in L2. Our degrees of freedom is not 5 here. I didn't report that. I should have. Our degrees of freedom here is what? 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 1 degree, 8 minus 1 is 7. So our degrees of freedom here is 7. I'm going to put a 7 in there, hit enter, calculate, and I have my answer. All right. So the do step, you're just going to copy everything down from the do step as we have in the past. Chi-square statistic, 5 degrees of freedom, 29.921. Our p-value, you'll notice your p-value is not 9.8. That's with an e -5. So you could write either 0.123498816. You could write 9.816 times 10 to the -5, or you could write squiggly line 0. I'd be okay with all of those. What we're saying here is, man, this is very small. I mean, we wouldn't expect it to be perfect, and this is pretty darn close. This is not pretty darn close. This is something that would happen very rarely if the null hypothesis were true. I mean, how often is this going to happen? Almost never. Degrees of freedom is 7. I'm going to report that. So what am I saying here? We would get deviations as large or larger than what we observed here. 1 out of 10, 100, 1,000. Is that right? 1 out of about 1 out of 10, 1 out of 100, 1 out of 10,000 times. 1 out of 10,000 times. Something that happens 1 out of 10,000 times. We say this is sufficiently rare to reject the null hypothesis. We're gonna conclude that the distribution of car color in Oro Valley is different from that in North America. Conclude, since our p-value is much, much smaller than alpha equals maybe say 0.05, we reject the null hypothesis. We have sufficient evidence to conclude the distribution of car color in Oro Valley is different from the distribution in North America. Boom. That is 11.1, chi-square test for goodness of fit. How well does this population match some specified distribution? We do that by comparing what we expected to see under that null hypothesis to what we actually observed. We calculate that chi-square statistic and we say, How likely is this? I will connect this back, excuse me, to the chi-square table. If we would have gone to chi-square um, 7 degrees of freedom, as this case was here, and we looked for a chi-square statistic of 29 point, what is it, 92. We look here, 7 degrees of freedom, and we scroll across until we find 29.92, and I see 29.92 is out beyond even 0.0005. We have a p-value even smaller than 0.0005, excuse me, so we could have rejected under any reasonable alpha there as well. You'll notice that the conclusion you make from your chi-square table and the conclusion you make from your calculator are going to be the same, but remember, your p-value is not ever going to be as specific coming from the chi-square table. That's what I've got for you. I'll have more on 11.2 next time. Take care. Have a good one.